Hey guys, welcome back to the channel and this new tutorial on Pytorch. In previous couple of videos, we learned about transformer encoder and decoder. In this video, we will combine both and implement our full encoder decoder transformer model. Okay, so let us dive in and see what components we need to implement. So if we look at the figure here, so we implemented this block which is encoder and this block which is a decoder. Okay, and we will try to implement this part as well as this part. So we already covered what is position embedding and how we generate them. Word embedding is simply like we use nn dot embedding module which accepts vocab size and the embedding dimension, and then in forward we simply add this scaling factor, and that's all in token embedding. So this is simply like we have created a class token embedding extending the nn dot embedding module, that's all. And in position embedding we just copied the code from the tutorial that we have created for position embeddings. Okay, in forward method we simply concatenate token embeddings with the position embedding as we have seen, as we can see here, like position embedding is added with word embeddings. Okay, so let us dive in and start with the generator. So this part linear layer plus softmax is called generator. So this accepts the output of the decoder, and then we have a linear layer which projects the decoder output into number of vocabs or number of words in the target vocab, and then there is a softmax layer on top of that. Okay, so still if it is not clear, let us implement and see how it looks like. So first let us implement the generator. So let us call class generator, and as usual we will extend nn module. So we need to import nn module, and let us define init. What it needs is vocab size and embedding dimension. Okay, and definitely we need to call super, and let us call self dot ff is equal to nn dot linear. What it accepts it vocab size and dimensionality. Okay, and now let us implement forward method. What it will accept is simply the decoder output, and it will simply return self dot ff, which is nothing but the logit, and also let us return the softmax output or the normalized output. For that we need to import a functional module. So we will simply say from torch.nn import functional as f, and what we will do is we will simply, so let us divide it into two parts. So here let us say logits is equal to self dot feed forward, and then here we can call f dot log softmax, or simply we can call softmax logits, and we will return logits, and that's our generator. So in generator we have simply a feed forward layer which converts or transform the decoder output to a dimensionality of number of tokens in the target vocab, and also we can return the normalized output as a softmax, which is a probability distribution. Okay. Now let us dive in and implement the whole architecture, call it encoder decoder transformer model. So let us implement that. It is fairly straightforward. So we'll call transformer encoder decoder. Okay. And as usual, we will implement an module. Let us define init. Let us call super. So init, what we'll accept is source vocab, target vocab, dimensionality of the model, num encoder layers, num decoder layers, and heads and dropouts. Okay, I think that's all. And what we need to create here is we will create first encoder layer, self dot encoder is equal to transformer encoder. So we implemented this transformer encoder. So what it accepts is simply the dimensionality of the model. So we will simply say d model, and what else is need is num heads, and heads we have, and num encoder layers, and that's all. And then we can implement decoder as well similarly. So decoder needs what? Transformer decoder, and what it needs is simply dimensionality of the model and heads and num decoder layer. That's our these two blocks, encoder and decoder, and we also need self dot source embeddings, which is nothing but token embeddings. And what it accepts is source vocab size and dimensionality of the model, and we can also pass the dropouts. And now we need one more thing, is we don't have dropouts. No, it is complaining. Okay, we don't have dropouts, so we need to remove that. And similarly, we need the target embedding as well. Target embedding will be of the size target vocab, and that's our target embedding. And also we will have self dot position embeddings, which is nothing but positional embeddings. Positional encoding, what it needs is embedding size, which is nothing but dimensionally of the model, and dropout. And that's our position embeddings also done. And next we need the generator. Okay, we simply say self dot generator is equal to generator, and what it accepts is the target vocab and the embedding dimension, okay, which is nothing but dimensionally of the model. And that's our whole init method. So what we have is we have a source embedding, which we will use in the decoder pipeline. We have so we have source embedding that we will use in the encoder pipeline. We have target embedding we will use in the decoder pipeline. We have position embedding that will be used in both encoder and decoder pipeline, this part. And then we have the encoder and the decoder, and then we have the generator part, which is nothing but this linear and softmax. Okay. Next, let us implement the forward method. So, forward method, we cannot implement everything in one method. So, we will divide it into three parts. One would be encode, and then we will have another one as a decode, and then we will have a generate, and then we will combine all three in one forward method. Okay. So, there is the requirement, that is why we cannot implement everything in one forward method, because during the decoding during the inference, we need to encode the whole input in one go, but when we try to decode, we will generate one target token at a time. So, that is why we need to split encoder and decoder part in two methods, which we will call encode and decode. Okay. So, let us implement it. So, we will define encode, which will accept source IDs and source mask. Let's call it none. And then first step is to create the embeddings, okay, which is nothing but we will call embedding is equal to self dot source embeddings, and we will pass source token IDs as source IDs, okay, and then we will again call self dot position embeddings, and we will simply pass the embeddings. Okay, so if you look at the position embeddings, so here we are doing the summation of token embedding with position embedding. Okay, and then we are applying a dropout on the added output. Okay, so that's done. Next, we will simply return self dot encoder embedding. Okay, definitely we need source mask as well here for the encoder, and that's our encode method. And then let us implement the decode. Decode is simply will accept target IDs. It will also accept the output of the encoder, which will be like, let us call it memory, and it will accept source mask and target mask. Let's just make it none so that we can run it without mask, and then we will create target embedding here. So, we will copy that code. So, simply we will use target embedding, and we will pass target IDs, and the position embedding would be exactly same, and we will return self dot decoder. So, what decoder accepts is the embedding and memory and source mask and target mask. Okay, and that's our decode method. And next, let us implement the generate. Okay, and generate will simply accept embedding, which is the output of the decoder. Tensor is equal to, or let us call it logits, is equal to Now we have generator, so we can simply return self dot generator, and let us call the embedding, and that's our generator. Now let us implement the forward method. So the forward method will simply accept source IDs, target IDs, and source mask, target mask. So let us make them none again. And first we will encode it. So let us call encode. What it returns is H, and encoded output, and we will simply call self dot encode. It will take source IDs and source mask. Okay. Now next is the decoder. So let us call H and decoder output, and we will call self dot decode. What it accepts is the target IDs definitely, and encoded output, and source mask and target mask. Okay, and next the last step is simply the generate, and we will simply return self dot generate, and we will simply input it to the decoder output, and that's all. That's our whole implementation of encoder decoder architecture. So now you have implemented the most powerful model in NLP industry or any other domain in that sense. Now let us test it out simply. So we will simply create a main. So what we'll need is we need dimensionality of the model, which let us call it 128, and let us say source vocab size is 1000, target vocab size is 2000, and let us create a dummy output. So let us call source IDs is equal to torch dot rand. So what we need is rand int. What we can say is low is equal to 0, high is equal to the vocab size, source vocab, and we need the size. Size is nothing but what we want to generate. Let us call it we want to have 2 sequence and of the length 30. Okay, and similarly let us generate target IDs, and it should be of the same batch size, but we can vary the sequence length. Let us call it 35, and it should be always with the target vocab size. Okay, and now let us create the model. So let us call model is equal to transformer encoder decoder, and what it accepts is source vocab size, target vocab size, dimensionality of the model, and let us call we want to have num encoder layers is equal to 2, and num decoder layer is equal to 2, and heads is equal to, let us call 2 again, and we need dropouts, let us call it 0.1. Okay, so that's our model also initialized. Next is simply we pass the source and target IDs to the model and see what we get the output. Okay, so what we get from the generator is two things. First is the probability, which is the output from the softmax layer, and then we have logits. So we will pass source IDs and target IDs. And now let us print the shape of the probability as well as log its. Okay, and let us run and see if what we implemented is correctly done. So let us run and see it. Okay, so the issue seems to be in generator part. Let us look at it again. What is the problem? Okay, so it is not correct, so it should be embedding dimension cross vocab size, and now I think it should be fine. Let us rerun and see it. Okay, you can see it works. So the only part it has a warning that we can simply remove because we haven't specified the dimension, and we always take it in dimension the last one. And let us rerun and see the warning is gone, and it is gone. Okay, so it is fairly straightforward. We just uh, looked at this diagram and then accordingly implemented it. Okay, so if still you have questions, ask in the comment section. I will try to address them further. So in the next video we will try to train the model for machine translation and see how well it performs. Okay, so thanks for watching. Bye for now. Take care. See you in the next.